Okay, here we go. We're going to dive into section 6.3, What is Trigonometry? This is for Foundations Math and Pre-Calc 10. I hope that by the end of the lesson that you're able to label triangle side lengths for right-angled trigonometry with a hypotenuse, opposite, and adjacent. I hope that you can explain what trigonometry is used for and how it works. I'd like you to be able to relate trigonometry to slope, and I'd like you to be able to set up trigonometric equations. Let's get started. First question, question number 24. Would you rather push a 20 kilogram box up the hypotenuse of triangle A or triangle B? Pause the video here and look at these two different situations and try to figure out which one you would prefer to push a box up and why. And then let's see if we can maybe find some quantitative ways to justify reasoning for either way. Pause the video here and go for it. Okay, hopefully you've had a chance to think about this a little bit and maybe identify why you would choose A or B. I'm going to look at some of the quantitative information and see if we can figure out why other people might choose that. On A, we have a height of 3 meters and a length of 11 meters. If we were to use the Pythagorean theorem, we'd be able to determine that the other side length is approximately 11.4 meters. And if we compared that to triangle B, we could see that the side length is 5.83 meters. So you might have chosen B because you're like, well, I'd have to push the box at a much shorter distance, almost half the distance, as you would with A. So that's one reason you might choose B. The other item that might play into what you're thinking about is how steep it is. And you can see that A is not as steep as B. If we wanted to have some sort of quantity or number associated with this, you may recall slope, which looked at the rise over the run of some sort of line. And we could compare that here. We would have 3 over 11, which is equal to 0.27. That's repeating. On triangle B, we have a slope of 3 over 5. That's not very readable. Which is 0.6. But by looking at these numbers, they don't really tell us that much if you don't fully understand slope and how it would relate to another measurement, maybe like degrees. So we are going to learn about a tool called trigonometry. What trigonometry would allow us to do, in this case here, would be to find out a measure of this angle here. We'd be able to determine that it's 15.8 degrees, and that for B, at the same angle, would be about 36.9 degrees. And these measures of an angle using degrees is sometimes more easy to relate to. And then you might say, well, I would choose A because the steepness of that is only 15.8 degrees, where for B, it's 36.9. It's more than double what A is. So that might be a reason to choose A over B. So two different ways to think about it. Your choice, of course, just a chance for us to explore different ways to compare these. This lesson is kind of difficult for us to be doing via video because there's lots of hands-on activities that we're going to do in class. This triangle investigation, each group was given a set of 8 triangles, and all the triangles had the same angle measures, although they were different sizes. So some were larger than others, but the angles were all the same size. So for example, you might have been in a group where you had a triangle that had a 90 degree and a 30 degree angle, and then the other angle was 60. So based upon the 30 degree angle, each of the triangles were labeled. So if this was your triangle and you were told that that was 30 degrees, the triangle would have been labeled with the longest side as the hypotenuse, or the side opposite from the right angle. then from this angle of 30 degrees, which we call our angle of interest, the opposite side will be labeled with an O, and then the side that touches the angle but is not the hypotenuse is the adjacent side. So those were labeled. I'll define them a little bit later on, but just so you have an idea of what those labels are. They were labeled for you so that you would know where to record the side lengths. For each of the 8 triangles, you needed to measure the 3 side lengths using a ruler and record those lengths here. Then what we were going to do, or what we did, was we would compare 2 of those side lengths. For example, we'd look at the ratio of the opposite over the hypotenuse. So we would take this side length here on triangle 1 and divide it by the hypotenuse. And that would give us a decimal value, or a fraction, and probably somewhere in the range of 0.5. We would go ahead and do the same for all 8 of the triangles. And what students quickly figured out was that almost all of those were very, very close to 0.5. And the same thing was done with the adjacent over the hypotenuse side length, and we ended up with something like 0.87. And that was the same for all of them. And for the last one, opposite over adjacent, was 0.58. Now these decimals that we're finding are the ratio of 2 side lengths. So one side length divided by another. And it's important to know which ones they're specific to what we're going to look at. We then went and opened up a program called Geogebra just to confirm that what we had done was correct. So the Geogebra applets look something like this. Not sure where everything wants to be in full screen right now, but that's okay. So you can see here we have a triangle, and I could adjust this to be like our 30-degree triangle I was talking about. And it doesn't matter what size of triangle you have. But if we were to look at the first one that we did, had the opposite over the hypotenuse. So if we go to Geogebra, we can see that this right now is showing you the ratio of the opposite side over the hypotenuse. And if you take the 2 side lengths, doesn't matter what they are, we end up with 0.5. And that's the same thing we calculated in class. So if when I'm changing this triangle, I'm changing the size of it, and I'm changing the side length of the opposite side and the hypotenuse side, but I'm not changing the angle. And that means that all of these different triangles are what's called similar triangles. Because they're similar, we end up with the same ratio. If we look back to our sheet, the second column we did was adjacent over hypotenuse. And if we look at the ratio of the adjacent side over the hypotenuse, you can see here we also get 0.87. Okay, so the idea was just to be comparing the ones we had in real life with this program. And the last ratio was opposite over adjacent, was 0.58. And we can confirm that that was the same as the ones that we measured. Then I was going to give students a chance to create another triangle of any measure in here. They could choose a 16-degree triangle if they wanted, and they would just tell me that they're going to do the adjacent over hypotenuse and that the side lengths were at a ratio of 0.96. And I magically would be able to tell them the degree of theirs. And I don't have the same applet in front of me, I just have a calculator. After we play around with this for a little bit, they're going to be amazed at the magic I have of being able to tell them the angle based upon the ratio of any 2 side lengths. It's really not that amazing, but it is an introduction to trigonometry and the relationships or the functions sine, cosine, and tangent. And that's what we would be looking at after. So after we had a chance to experience that, we would notice that the ratios are all the same for any triangle. And then I would go through and talk about that a little bit, and I would introduce these functions. First one being the sine function. It's actually spelled S-I-N-E. And the sine function relates the opposite side and the hypotenuse side. The cosine function, we learned, relates the adjacent and the hypotenuse. And the tangent function relates the opposite and adjacent. And these, when they're written as an equation, we just use the abbreviated version of sine, so S-I-N. We don't say sin, we say sine still. And then there's some sort of angle, and I'm just going to represent that angle. In our example, it was 30 degrees. I'm going to use this Greek letter here, theta. And we know that the sine of that angle is equal to the opposite over the hypotenuse. Same with the cosine, we shorten it to the first three letters. Cosine of any angle in a right triangle will be equal to the adjacent over the hypotenuse, and the tangent of any angle theta will be equal to the opposite over the adjacent. So this exploration was just an opportunity to see that if we have similar triangles, we have the same ratio of sides, or each triangle with the same angle, and we can calculate those using our calculator. We used to have trig tables in the old days, but now our calculators are able to do these calculations for us. I'm going to take a few moments and just define a few pieces that I introduced earlier. When identifying the side lengths for trigonometry on a right angle triangle, we use the terms hypotenuse, which is the longest side, of a right triangle. You can also think of it as being across from a 90-degree angle, or the right angle. One of the other side lengths is the opposite, and it's this side opposite the angle of interest. And the adjacent side is the side that's touching the angle of interest. So if we have some right triangle and we have an angle of interest, either the angle we know or the angle we're looking for, we can then label the sides. The hypotenuse doesn't matter where the angle of interest is. It's always just the longest side. But the other two do matter. And if we start with the opposite, we would go from our angle of interest and go straight out. That would be the opposite side. And the side that is touching the angle of interest would be the adjacent. This is our labeling scheme, and it helps us know what sides are in which ratio for the trig functions. If the angle of interest or the target angle changes, does the naming of the sides change? So not the hypotenuse, never changes, but the opposite and the adjacent would switch. So for example, if I drew the same triangle below, This side here would still be my hypotenuse, no matter where my angle of interest is. But if I move the angle of interest to be here, then the opposite would switch to be this side down here. And the adjacent would be over here. So depending on where your angle of interest is, that will determine where your opposite and your adjacent sides are. Can the target angle be the right angle? No. Okay, so the target angle is, the right angle is always 90 degrees, and the trig ratios are not set up to function with the target, with the right angle. So the target angle or the angle of interest must be one of the other two angles. So let's label some of these triangles here. Label the sides below using the hypotenuse, opposite, and adjacent relative to the angle of interest, or the target angle. So here is your angle of interest. We know that the hypotenuse is always the longest side. Then from our angle of interest, straight out, gives us the opposite side. And the one that's touching our angle of interest is the adjacent side. I'm going to let you stop the video here and go ahead and finish these up on your own.